Good afternoon. IF members and distinguished guests, I want to welcome you to Climate Day here at the IAF. We had a very interesting session this morning that dealt with climate change in many different aspects of it. For the plenary session number 6, this session today, we're actually going to take a different tact. Instead of trying to cover many topics, we are going to choose instead to focus on one topic. And that topic is the carbon cycle and its impact on all of us. In particular, we're going to look up at the buildup of CO2 in the atmosphere, and we'll examine how this one measurement cascades through our society. This plenary is entitled Carbon Monitoring from Space and What It Means to Us. We'll examine the relationship between global carbon dioxide monitoring and how it connects to the climate change, mitigation, and adaptation strategies and decisions that we have to make. Let me first set the stage. Basically, a carbon cycle involves an intricate dance that really goes on between the oceans, the land and its vegetation, as well as the atmosphere. And into this waltz is cutting a human-contributed 6 to 8 gigatons of carbon per year that is disturbing the equilibrium. We fully don't understand all of the sources and the sinks of the carbon cycle, but yet we are being forced to make critical decisions right now. And if we don't make them now, the implications can be very large in the future. For us to understand the impact of this rise of CO2 in the atmosphere, it takes a new coalition, a group of researchers and scientists that are out actually making the measurement. They have to make sure that the measurement they make has sufficient calibration and validation to have validity. They have to make that information widely accessible, and they have to make it accurate and over a long period of time. Coupled with those individuals are also modelers. They're ingesting the data, they are actually creating the models, and they're trying to predict the future. They're trying to show what will happen at different timescales. Extraordinarily difficult thing to do. They have to do it on a on a physical scale, on a temporal scale that is both small and large. And they have to do it in a manner that is transparent and that is scientifically credible. And lastly, the third group is the decision support and the decision makers, those that have to take action. They have to do it on a national and international level. They have to do it with policy implications and economic implications. And they have to make sure that everyone, all the countries, buy in. This is a very interesting group now that really has not come together in the past. And what we have tried to do today is to bring representatives of each one of those groups here on the stage to talk about what they are doing and to be able to interact with one another about the roles that each of them are playing. Let me go ahead now and introduce first myself. I'm Jim Graff. I'm the moderator for this session. We have Dr. Moriyama, who is from JAXA, and he is chair of the CIS Global Carbon Task Force. He also has been affiliated with the GOSAT calibration and validation activities since the inception of the mission. We have Dr. David Crisp, who's the principal investigator of the OCO mission. He's from NASA, and he will be talking about OCO and some of the other measurements that are being made by other spacefaring countries. We also have Dr. Inouye. And Dr. Inouye represents the modeling community. He's the GOSAT chief scientist from the Research Institute in Humanity and Nature. We also have other distinguished guests from a different side. The last three that I've talked about we're familiar with, but we have some two individuals that have come to us that represent other ideas and other points of view. Dr. Vladu is coming from the UN Framework Convention on Climate Change. He's the manager of the Analysis and Methods subprogram, and he brings with him policy understanding and what's happening in the political realm and what the constraints are and what they're looking for. Complementing him is Dr. Lee from South Korea. He is the vice chair of the IPCC. He's dean of engineering at Kim Young University. And he will bring with him some of the economic implications of either making a decision or the converse is not making a decision. So we've brought all of these gentlemen here today, and what we intend to do is let each one of them have a statement about 6 to 7 minutes long, and then we are going to have a discussion up here on the stage with some questions that we have, and then our intent is to open it up to questions from the audience. We will use the microphone so you don't have to write the questions down, but if you are going to ask a question, I ask to keep the question concise, and I'm asking the responders to also do the same so we can get through them. I'm hoping we will have time for questions. If not, the panel members will be available after the session to answer some other questions. So with that in mind, I'd like to turn it over to Dr. Moriyama, who will talk to us as one of the data providers and the measurements. Dr. Moriyama.
Thank you very much. Distinguished participants, ladies and gentlemen, it's my honor to have an opportunity to explain about our GOSAT, our achievement, and also I'm serving the co-leads of GEO carbon tasks, and also the CEO's Committee on Earth Observation Satellite, our carbon task force. So you can see, okay, you can see on the upper left. Thank you, David. Okay, so you can see upper left. So this is GOSAT global data set from August the 1st to August 31st. This is the 1 month average. But this is still not well validated, but we are underway to calibrate and validate the GOSAT data to distribute level 1 the end of this month, and also the level 2 will be the end of next January. So we are underway to calibrate and validate this kind of global measurement of column amount of CO2 and methane on a whole global level. And we are collaborating with NASA and also the NOAA to mature our level 1 and level 2 products to be distributed. So this is global data sets created from AIRS. This is a NASA instrument and working very well. So we are now trying to combine or to combine those space measurement to demonstrate how usefulness the space measurement for global carbon monitoring from space. So these are our achievement of GOSAT, and also we are trying to demonstrate these kinds of new satellite measurement in coming GEO6 plenary in next month, middle of November in Washington, D.C. That's the opportunity of GEO6 plenary. And also UNFCCC COP15 in Denmark this December. So we are now finalizing to integrate this kind of space measurement output to demonstrate. And also, yes. We are now working together with our international partners. So there are two major bodies dedicating to the global carbon measurement. The first one is GEO. GEO is a group on Earth observations. So this is a very huge international community by involving the ministerial level participant from 18 number of countries. So GEO carbon task goal is to implement a global carbon observation and analysis system addressing the three components of the carbon system. Those are the atmosphere, land, and ocean. And GEO, Carbon Community of Practice, is now underway. And formally, we will establish this new community of practice next month at the GEO6 plenary in Washington, D.C. And also at that time, we have a chance to have a 3-hour side meeting in parallel with plenary. And we are really expecting fruitful discussions to accelerate our activities dedicated to global carbon monitoring. And also the other international organization is the CEOS, a Committee on Earth Observation Satellite. So this March, the CEOS SIT chair approved to start up the CEOS Carbon Task Force. So this Carbon Task Force is working together with NASA, NOAA, ESA, and other space agencies and the science communities to demonstrate the usefulness of satellite measurement and also create their so-called fusion data set for global carbon monitoring. So we are now underway operating and the calibration and validation for GOSAT. And also we have a very nice whole globe data set by Skiamachi and also from the AIRS, YAZI. And also our task force is focusing the next future of greenhouse gas measurement from space. So David will explain about the future of greenhouse gas measurement in space. And also our GOSAT will be also expecting the follow on the mission, continuing the measurement. And these are the very important contributions to the global carbon communities. And now we are on the way to publish the GEO carbon report, which is updated the former IGCO carbon team report, which is published in 2004. And version 1 will be distributed next month in plenary, GEO6 plenary. And also final complete version will be December UNFCCC COP15. Thank you very much.
Thank you, Dr. Moriyama. Dr. Crisp?
Good afternoon, everyone. We're entering a new era when we're going to have an opportunity to be making measurements of carbon dioxide and other greenhouse gases from space with the kind of sensitivity, resolution, and accuracy needed to actually support decision support for decision support purposes for our policymakers. This is a brave new world, and what I'd like to do to start with is to give you an idea of a roadmap that brought us to where we are today and where we have to go in the future to actually fulfill the promise of all of these new great observations from space. First of all, I'm starting with the Skiamachi instrument on the Envisat. This instrument was flown back in 2002, and it can make measurements of both carbon dioxide and carbon dioxide and methane from space, two of the most important greenhouse gases. This was not the major objective of this particular mission. Mainly, it was worried about air. It was launched in order to monitor air quality issues, but it was able to measure both carbon dioxide and methane. It's made measurements now over a number of years, and they're shown here. Notice the variations in CO2 over the seasonal cycle. Every spring and summer in the northern hemisphere, CO2 is pulled out of the air as plants grow their new leaves. In the fall and the winter, it gives that up and so forth. And you see this cycle going in and out every year. And the dots on this plot actually show some results from Skiamachi plotted against that curve. It's actually making measurements that are good enough so that they're recognizable as measurements of carbon dioxide, but it's not telling us very much about the Earth right now. As we look at it, you can basically, you have to integrate over seasons or full years in order to get good CO2 measurements at this point. But I want to point out that this was not the last CO2 monitoring mission we're ever going to fly. This was the very first, and it was a real groundbreaker, and we've learned a tremendous amount from Skiamaki over the years, both in its measurements of carbon dioxide, shown here, and measurements of methane. So it's been a real breakthrough. In addition to that, at about the same time, we launched the AIRS instrument on the Aqua platform, and this used a different technique. Whereas Skiamaki looked at the absorption of sunlight by atmospheric carbon dioxide and methane, the AIRS instrument actually measures carbon dioxide in emitted thermal radiation. And it's now making complete global maps of the Earth every couple of days, and we're getting very good results. But these results are referring to the carbon dioxide at altitudes in the 5 to 10 kilometer range. So up where airplanes fly. The primary asset of this is it gives us a direct measurement of carbon dioxide at those levels of our atmosphere where it's most effective as a greenhouse gas. We can actually make a direct measurement of a greenhouse gas and the greenhouse effect using AIRS data. More recently, the IAC instrument was launched on MEDOP, and it's going to be carrying on this class of measurements as well. It's been making, as I pointed out earlier, though, AIRS has been making measurements over a number of years, and they're being fairly well validated, and they're, as I said, giving us a very good story for measurements and maps of CO2 at an altitude in the atmosphere where we've never been able to make those measurements before. So a big step forward, too. But we're not at the end of the road. We still have some improvements that we need to make in order to actually meet the true promise of these observations. In particular, the measurements that we're making today require greater sensitivity so that we can detect small changes in carbon dioxide, greater accuracy so that we can rely on those measurements. We need better coverage. Both the Skiamaki instrument, for example, makes measurements only over land, not over the oceans. We need to measure both clearly, and we need higher spatial resolution. All of those are illustrated here. I'll take just a second to go through some of the justification for those. First of all, in this first map, this is a map of the world. This is a map of CO2 that was generated by a model. But the important thing to say is that from the bluest blue, the darkest dark blue here, to the brightest reds, there's only a few parts per million variation in carbon dioxide. The bluest blue is 372 parts per million. The reddest red is 380 parts per million. That's 8 parts per million out of almost 400 parts per million. That is 8%. Or, sorry. I'm sorry, 2% end to end. So basically we're seeing a sum total variation across the whole world of 2%, and our measurement systems must resolve that 2% variation. And if I want to measure the difference between, say, Korea and Japan here, the variation in carbon dioxide in our atmosphere is less than a half of 1 part per million, which is a very, very hard measurement to make. Now, in addition, as we look, this is aircraft measurements across the Earth. Once again, a very, very small difference. And what we're looking for is these places where you see the large difference in carbon dioxide. That's where something is either emitting carbon dioxide or reabsorbing it. Our systems have to resolve those small effects too. Those are also less than 1 part per million. And I've overlaid on that the measurement precision of GOSAT, shown here, and what we hope to do with OCO in the future. We need to make measurements that are sensitive close to the surface with near-infrared measurements such as Skiamaki, GOSAT, and eventually OCO. We hope to be making measurements near the surface. With AIRS, we make measurements up in the upper atmosphere. These measurements are the near-surface measurements are far more valuable for measuring sources near the surface, such as emission sources from human sources, also sinks. There are places where CO2 is being absorbed. Once again, accuracy, we need to make very, very careful comparisons between the space-based measurements and our available ground-based measurement capabilities to ensure that the measurements are truly accurate. A small variation in accuracy from pole to pole would imply the presence of a sink that isn't really there or a source that isn't really there. We have to get them very accurate. Finally, coverage. Nadir observations give us high resolution. You need glint observations over the ocean, though, because you just don't get any signal. Finally, higher spatial resolution is critical in order just to get measurements even in cloudy regions. So with that, I'll stop and turn over to the next speaker and introduce Dr. Inouye.
Thank you, Dr. Crisp. Dr. Inouye. Now, the first two speakers have been representing the data producers. Dr. Inouye will make the transition and talk about the modeling community and what they're doing with the data that you're hearing about from the first two speakers.
Hello, gentlemen. To tell the truth, I was against the greenhouse gas measurement from space before, 10 years ago. And we made a lot of effort to measure carbon budget on surface. But I gave up to expand this type of measurement all over the world because it takes a lot of it needs a lot of effort and sometimes impossible to expand. And six years ago, I proposed GoSat project to JAXA, and it is now realized. And still, there is a lot of problems, but very promising data is being obtained. The carbon community did a lot of effort to measure the ocean carbon balance measurement, land biosphere carbon budget, and it is not written here, but the human emission, fossil emission. This is fairly well known, so scientists did not pay so much attention to it. And based on these two components, it is possible to calculate the atmospheric concentration distribution combined with the transportation model, wind field. And atmospheric measurement exceed to the carbon budget study by 10 years. As you know, the CO2 observation was started at Mauna Loa by Dr. Keeling, and we found a very clear seasonal variation and trend to increase by 1% per year. And such a atmospheric observation network expanded, and it can be comparable with the data from the bottom-up approach, and discrepancy was discussed. After expanding the atmospheric observation, the new method to evaluate the sink and source distribution from the atmospheric measurement was started. It is about 5 years ago, or almost 10 years ago. And now, combining these activities and adding satellite data aspiration system will be established soon. The principle of the top-down approach is very simple. When there is a wind flows in this direction, and there is a sink, the concentration of carbon dioxide decreases, and vice versa. So the interaction between the land surface and atmosphere gives a change of the concentration in the atmosphere, CO2 concentration in the atmosphere. So we can calculate the sink strength from such a change. But this is too simplified because the practical transportation wind field is very complicated, and there is not only the horizontal transportation but the vertical transportation and mixing and so on. So we need to do the calculation globally. This is the model calculation. Upper 2 is the computed carbon dioxide concentration. Left is winter in northern hemisphere, and right is summer. And down two figures flux inverted from the concentration distribution. If the CO2 concentration distribution can be obtained exactly without error or noise, and if the transportation of atmosphere is perfectly known, we can do the calculation very exactly to determine the sink and source distribution on surface. Excuse me. But unfortunately, the observation has a systematic error or some lack of data, and transportation model is not perfect. So we need to do a lot of effort to improve it. This is a very preliminary result of GOSAT, and upper is the carbon dioxide and lower is methane concentration distributions. As you can see, the observation does not cover fully over the land and ocean, and it is because a lot of part is covered by cloud. And if you see this figure, very strange is the concentration here over the Greenland is very low, and concentration in Africa over Sahara, high concentration is observed. This is the because of the systematic error of the surface altitude evaluation and the process of the multi-reflection caused by aerosol. If the aerosol exists, in general, the light is scattered, and CO2 below the aerosol is hidden. But in the case of the very bright surface, like a desert in Africa, much reflection occurs. Reflected light is reflected again from the surface, and total path length is increased so much. So anyway, there is a systematic error in these two areas. So I want to mask this part. Then other part is very reasonably explained. Southern hemisphere shows a lower concentration, and the northern part shows a higher. This is very consistent with the past observations and model calculations. And you can see a higher concentration in some area, for example, in Europe, in China, India, and east part of United States. These are due to the very large emission from this area. Anyway, from such a data, we can discuss more about the global carbon budget. But we can apply this type of data to identify the point source strengths, such as mega city, big city, forest fire, or very large leakage from natural gas pipeline. We are studying the forest fire emission, for example, in Indonesia, Kalimantan. Here, it is not a simple forest fire, but a peatland fire. So the carbon accumulated in past thousands of years is being emitted by fire. The natural gas leakage causes accidental explosion sometimes, but it emits a lot of methane in the atmosphere. Several megaton of methane is emitted from one compressor station per year. This is a very huge amount, but it is not fixed and continue to export such large amount of methane. We want to study such a point sources as well. Thank you very much.
Thank you, Dr. Inoue. And now, representative from the United Nations, Dr. Vladu will talk to us about what it means in terms of the policy the policy decisions that we have to make.
Thank you, Jim. Ladies and gentlemen, thank you for the opportunity to address you. All over the world, people are aware of the dangerous consequences of unmitigated climate change. Sea level rise, severe storms, floods, prolonged droughts, and water shortages will affect us all. The world's opportunity lies in limiting climate change, in finding solutions that will propel us in a safer future. You have come to this plenary session to think how we can inform climate change mitigation decisions through global carbon monitoring. We have heard from previous speakers on opportunities for improving data and information and means to enhance the availability and supply of such data and information. In my presentation, I will focus on how Earth systematic observation is supporting and could support in future decision-making in the intergovernmental process on climate change at the international level. 2009, the year of climate change, is set to culminate in an agreed outcome on strengthened climate change action in Copenhagen in December. In his opening address to this Congress, the Secretary General of the United Nations, Mr. Ban Ki-moon, said that this agreement has to enable an ambitious, fair and effective international response to climate change. The Secretary General summarized at the high-level summit on climate change held on 22nd of September 2009 the following as essential political components of the New Deal to combat climate change. First, enhance action to assist the most vulnerable and the poorest to adapt to the impacts of climate change. Second, ambitious emissions reduction targets for industrialized countries. Nationally appropriate mitigation actions by developing countries with the necessary support. Significant scale-up financial and technological resources and equitable governance structure to manage the generated support. Systematic observation are particularly important for the first 3 points which I just enumerated. In the run-up to Copenhagen, parties are negotiating cooperative actions to enhance the full, effective and sustained implementation of the Convention under what is called the Bali Action Plan. The main areas under consideration, which you can see on the view graph on the bottom part, are a shared vision for long-term cooperative action and enhanced action on mitigation of climate change, adaptation, technology development and transfer, and provision of financial resources and investment. Parties are also negotiating future commitments for Annex I parties under the Kyoto Protocol for the period beyond 2012. The protocol provides for legally binding targets for emissions of 6 major greenhouse gases in industrialized countries and international market-based instruments that created a new commodity, carbon. Just before coming here, parties, before you started your Congress, parties convened in Bangkok for a round of negotiation, which will be continued in Barcelona in November, the last session before Copenhagen. Negotiations are advancing and, as some said, the ingredients for the agreement are now on the table. Now, let me turn to systematic observation. Earth systematic observation and climate modeling are playing an important role in achieving the ultimate objective of the Convention, which is stabilization of the greenhouse gas concentration in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. An integrated framework for addressing climate change shows complexity involved and the linkages between socio-economic development paths, atmospheric concentration of greenhouse gases, the climate system, and the human and natural system. To achieve the objective of the Convention, accurate and reliable data with enhanced resolution and coverage are needed on, for example, concentration of GHGs, temperature, precipitation, and sea level rise. And improved models with enhanced regional resolutions are needed to predict current and future behavior of these systems. In this connection, IPCC, in its fourth assessment report, noted significant progress in the understanding of the past and recent climate change, arising from large amount of new data, more sophisticated analysis of data, improvements in the understanding and simulation of physical processes in climate models, and more extensive exploration of uncertainty ranges in model results. Having all this data and information, and what science tells us, informed decisions could be made on mitigation and adaptation. Now, how is scientific information flowing into the convention process? Oops. I have here the models and the data. In our process, the assessment reports of the IPCC are the main source of scientific information that support decision making. For example, the political options that are currently being negotiated on the long-term global goal for emission reductions under what we call the shared vision, part of the Bali Action Plan, use IPCC information and concentrate around the following major concepts: the level of stabilization of GHG concentration into the atmosphere, limitation of temperature increase, the level of global emission reduction, and peaking time of GHGs. Our data information is needed to support development of various methodologies for mitigation. For example, data on forest coverage is needed to establish reference emission level for deforestation and forest degradation. Forest monitoring systems can use a combination of remote sensing and ground-based forest carbon inventory approach for estimating anthropogenic forest-related greenhouse gas emissions by source and removal by sinks. Such information could come from various other organizations, such as you have here COs and CO carbon, and we heard here about carbon task forces, which are set up and will provide such data. Agriculture and land use in general has been another important topic in the negotiations as regards both mitigation and adaptation, but emission estimates are uncertain and limited information is available for establishing baselines. Further constraints include high cost of measurements and monitoring of emissions reductions and the lack of capacity and tools to enable accurate and direct measurements of, for example, carbon in soils and methane emissions. Carbon capture and storage is another emerging technology which could also benefit from measurements of CO2 emission limitations. Now, some final thoughts. Mitigation of climate change needs to be based on reliable information on sources and sink of greenhouse gases. To ensure this, observations are needed to verify the changing distribution of GHGs, gases and sinks. The implementation plan for the Global Observing System for Climate in support of UNFCCC calls for a number of actions to maintain, strengthen or otherwise facilitate global observations through a set of essential climate variables. High quality measurements of atmospheric composition ECVs, both in situ and space-based, need to be strengthened to better understand and predict the effects of climate systems and to underpin policy level abatement and mitigation measures. As regards the satellite system, improved instruments, international coordination and exploration of databases have led to an increasingly important contribution to global climate monitoring. I still have 2 points, can I make it? Okay. In our process, the SABSTA encourage coordinated implementation of cost-cutting space-based components of GCOS and continued over long term, including the continued contribution response to the needs identified in the GCOS implementation plan through COs. Our process further welcomed the commitment of COs member agencies to work towards improved availability of current and future data for forest carbon monitoring. We look forward to working with you and receiving from you the information we need for making informed decisions. I am sure that this week you will make significant progress towards strengthening the contribution of space agencies to tackling the issue of climate change. Thank you.
Thank you, Dr. Vladu. Dr. Lee?
Thank you. Very briefly, let me say something about the IPCC. Its mandate is to provide scientific, technical, and socioeconomic information on all aspects of climate science, impacts, and response strategies. We do provide assessment reports and many other relevant papers, and our goal is to provide policy relevant analysis, not policy prescriptive piece of the analysis. Our work goes through a very rigorous peer review process and adoption approval by all member governments, especially the summary of policymakers has to be approved by 192 member governments. The first assessment report in 1990 provided key inputs leading to the establishing the UNFCCC in 1992, and the second assessment report, 1995, provided the scientific basis for formulating the Kyoto Protocol in 1997. Third and fourth assessment led to the formation, the configuration of the Bali Roadmap. We are right now at the process of producing the fifth assessment report. We believe this will contribute to the post-Kyoto regime and beyond. 2 years ago, IPCC received a Nobel Peace Prize, and this is for our efforts to build up, disseminate knowledge about climate science, and also our effort to lay foundation for measures to counteract these changes. I have two charts here. One upper one is the temperature. The bottom one is the upper one is atmospheric concentrations, and bottom one is temperature change. 15 degrees C, that is the average current Earth temperature. I want to highlight several numbers here. The top 180 and 300 ppm. This is the range of CO2 concentration during the last 400,000 years, measured by the ice core data. Now, right now, as you know, the atmospheric CO2 concentration is about 370 ppm. Therefore, the current level of concentrations is unexperienced, at least for the last 400,000 years. Now, the 2 to 3 degree temperature, you have heard attempt to limit the temperature increase to 2 degrees C, and it happened 3 times for the last 400,000 years that the Earth temperature rose 2 to 3 degrees compared to current level. It took 10,000 and 20,000 years to increase 2 to 3 degrees from the current level. From the current level means 15 degrees C. Now, the IPCC, various reports, including third and fourth report, indicates that for the next 100 years, the warming will be at least 1.8 degree up to 4.0. Some scenarios suggest 4.5 degrees C. So this is a very, very rapid, extremely rapid increase of Earth temperature. Obviously, this will bring threats to the climate system and attending the threats to ecosystems. This is a very famous diagram, burning amber diagram, reported in the IPCC third assessment report. And this, to the various categories of threats, you have the gradients of temperature changes. As temperature rises, threats to various categories of impacts will get much worse. Meaning of 2 to 3 degree threshold, research generally shows that the species, 10 to 40% of species face threat of extinction, and most importantly, the vegetation will become CO2 source rather than a CO2 sink. This is a very serious transformation. And then, as you know, food production, water, and extreme climate events will all get very severe and frequent. Now, what is the cost of this climate damage? We have a very large ranges of the estimates. IPCC fourth assessment reports that for the doubling of CO2 concentration in the atmosphere, the GDP loss will be between minus 1.6% and 2.5%. This is the reports produced two years ago. On this diagram shows that as temperature increases, the threats, the GDP loss in terms of damages will certainly increase. It shows the shape and the rate of change there. Now, the 2001 IPCC report says that the GDP loss will be around between 1 and 5%. 3 years ago, the Stern report that the loss loss to GDP will amount to somewhere between 5 and 20%. Now, 20% is very, very large number, and in many surveys in many researches of the cost of climate damages, this 20% is mostly the very extreme value. Now, there's a second way of measuring the cost of climate damage. This is the so-called the social cost of carbon measurement, dollar per ton of CO2. And estimates report that for 2005, currently it should be around $12 per ton of CO2, and for 2050, it will rise to something like $23 and then $50 in 100 years from now. Now, these two measurements, cost estimates of both GDP losses and social cost of carbon, have very large potential for underestimation because of the inherent uncertainty in climate sensitivity of between 2 and 4.5 degrees C, and then obviously a non-linear climate transformations, which will be beyond the realm of estimation, and then obviously you have to monetize the non-market impacts. And then how do you treat the value of life? That's a very sticky question. And then because of this 100 years of damage occurring in the future, discount rate figures very importantly in these final calculations. Now, this chart is about the cost of CO2 abatement. In other words, how much would it cost to reduce the CO2 emissions? Again, there are two types of measurement. One is GDP loss, second is the CO2 price. The GDP loss relative to the reference case. Reference case means the world without any climate change policy, the world with continued use of fossil energy. For 2003, the loss of GDP will be about 2.5% in order to reduce the CO2 mitigation. And then 2050, 4.4%, and 100 years from now, it will be about 6.5%. Now, in terms of CO2 price for 2030, the highest number will be $79 per ton of CO2. Now, if you remember the CO2 price in the EU trading market, it fluctuates between something like between €8 and something like 25 euros per ton of CO2. Again, I want to emphasize that these two estimates are subject to a very large degree of underestimation due to the assumptions of a global participation. In other words, all countries participate in the reduction of CO2, which is very unrealistic assumptions, I think. And then transparent markets, which means there's no uncompetitive behavior in the markets, and zero transactions cost. This means a world without any lawyers and accountants, any trade disputes, etc. And then this kind of model obviously assumes a global carbon tax or global cap and trade system. Researchers estimated how much a penalty will occur if there will be only a partial the participation. If only 5 big emitters participate in the abatement effort, that 5 countries will be China, US, EU, Russia, and India. Then the associated penalty, that is percent cost of the cost increase relative to the cost of universal participation, it will be 114% increase. Now, if 10 countries, 10 big emitters participate, those 10 will be Big 5 plus Japan, Canada, Korea, Iran, South Africa. Then the cost penalty will be 61% compared to a global participation. Now, if Big 25 participates, then the penalty will be 50%. That means the cost shown here can very easily more than double when you consider a situation where a less than full participation occurs. However, there is a possibility of decline in abatement cost. Now, the BAU, the business as usual scenarios, already incorporate large potential for technology improvement. In fact, the IPCC report shows that the more the BAU emissions, the higher the abatement cost. In reverse, the less the BAU emissions, your cost of abatement will be much less because you have already factored in the potential for the technology improvement in the energy efficiency and fuel substitutions. And then if you have a spillover effect, you have a spillover effects from most of R&D effort. And if that spillover effects in low carbon energy technologies are more than other technology R&D, then you have a positive effect. So there's a positive effect. Now, the climate change policy has to go through a number of steps. First of all, you have to agree on the stabilization targets, and then you have to agree on the carbon budget, and then you have to agree on the annual carbon budget, and then the most important and difficult one is that you have to agree on the allocation of the annual carbon budget among the countries, and then you have an implementation system have to be installed. Now, I think summing up, the climate change costs and CO2 abatement costs are subject to very large uncertainties, as you saw. However, uncertainty should not be reason for inaction. One has to consider the portfolio approach, which consists of mitigation, adaptation, and R&D. R&D is the one to reduce the range of uncertainties. And in the process, you have to consider market-based approach, carbon tax, or cap and trade is a instrument that you have to consider in tackling this mitigation, adaptation, or R&D in a most efficient way. And then largely this overarching principle of this climate change policy is precautionary approach. You're adopting the hedging strategy. Thank you very much.
Thank you, Dr. Lee. I'd like to, we're running out of time, so I'm going to quickly start the discussion with some of the panelists here. Let's start with a question. We have organizations creating data, we have organizations modeling it, we have policy decisions and economic decisions being made. Who is system engineering all of the process, or who should be system engineering the process? And throw it open to the panel here. Who would like to try to take a first crack at that?
Okay, so as for the space measurement, I myself and David indicate that some example of the global measurement from space. But now, right now, unfortunately, we have no exact scheme to coordinate, to make harmonized observations to integrate those output to the science communities. So one thing we have to consider is the harmonization of their independent measurement. And also in the future, like CO3s, such kinds of constellation measurement is one of the key to improve their measurement, and not only the accuracy, but also the occasion of their greenhouse gas from the whole globe. So such kinds activities should be becoming much more important in the future. And also, we are now wondering the next step of their measurement. So GOSAT is now considering the next step, and also maybe David is now the person in charge to consider the OCO alone. So I think this is my personal opinion that the next decade we have to continue our passive measurement like a Fourier transform spectrometer and grading spectrometer, and in advance maybe much higher accuracy measurement capabilities like laser atmospheric sounder and also the differential absorption lidar sound.
Thank you. Would anybody else like to try that question? Dr. Fladu or Dr. Inouye? You know, who do we get to do the modeling? How do we know that the data that's being produced is going to be used appropriately and will be useful, let's say, to decision makers?
I think the improvement of or increase of data help our understanding, and the model will provide more precise and more spatially resolved results, and this will contribute to the policy makers. For example, there is there is a reporting system of emissions, but in the developing country, most of them use some standard emission rate multiplied by the area, and their reporting is not so exact. We want to evaluate such a value from the observation data and model analysis and contribute to a better understanding of the emission inventories. I think the more data accumulated during the 5 years mission of GOSAT provides a much better understanding of such emission inventories. But there is an area where the satellite observation is very seldom. For example, the polar area and the very cloudy area. So in such an area, we need a ground-based observation as well. So I don't say the satellite observation solve all the problems, but it contributes a lot. But I want to emphasize that other activities is very important as well.
Thank you. Flora, would you like to?
A short point here regarding the verification and monitoring. Yeah? Of course, up to now, because there were no systems to measure directly CO2 emissions, the monitoring is basically done to national GHG inventories, which are constructed based on assumptions using guidelines from IPCC, data from fuels, emission factors, multiplying activities, this kind of approach. The fact that such data will become available will open another possibility, which means to really monitor real data of CO2 emission, which may bring some different dynamics in the negotiation of these things. Thank you.
Thank you. Let's ask Dr. Lee, what, as IPCC, what do you expect from the data providers, let's say, in terms of calibration, validation, and coverage?
Complete data is an ideal situation. I think even with the current inventory of data and information, the message from the scientific community to the policy makers are very clear. We have to act very immediately. In my thinking, there is more cost of waiting better data than starting with policy with incomplete data. The climate change decision is a decision under uncertainty. It has to be an iterative process, and it is essentially a sequential decision-making process because the future is uncertain, and you have to iterate toward a better decision. You need to make a mid-course correction because new information will be available in the future as you expect a better product from your research. I think the whole process is a risk management process, and policy makers need to have a better data and information, but they don't have to wait for better data and information. They have enough information at this time to act and then learn.
Thank you, Dr. Lee. We're running out of time. I'd like to ask one more quick question of Dr. Crisp. I think there'll be a question out there that says, tell us about the possibility of a reflight of OCO.
Okay, as all of you know, we lost the OCO mission in February when the launch system failed to make orbit. Almost immediately, we came up with a plan to rebuild the mission, showing NASA that we could rebuild the mission and be ready to fly in less than 30 months from the authorization to proceed. We have since convinced just about everybody, and everybody has come to the conclusion within the U.S. government that we have to do this again. We're still trying to identify the resources to do that. There's a little bit of uncertainty on when we will get started, but the uncertainty now is measured in months. And we're hoping still as early in 2012 to have the OCO instrument up there again as our next generation carbon dioxide monitoring system. I look forward to it.
Thank you, Dr. Crisp. I'd like to thank all of the panelists for their time and for the energy that they put into making the presentations. And I'd like to thank you, the audience, for staying with us. The panelists will be available for additional questions if you'd like to come up, and we appreciate the attendance. Thank you.